Assalamualaikum, I'm Dayang Fazwin.
Hi, I'm Najiha.
Hi, I'm Dayang Munira.
I'm Amira Azman.
I'm Aswardiana.
I am Zahira.
Real-time measurement is one of the preferable methods to measure granule size as it is not time-consuming and can measure a wide range of particle in size. Particle size and particle distributions are two important parameters in drug formulations. This is because it can affect tablet weight variation, tablet porosity, and dissolution rate. There are many applications in industry that use this method such as crystallization, coating, semi-solid formulation, and granulation. Real-time measurement has four basic options which are offline, online, inline, and at-line. But in these presentations, I will only emphasize on offline, inline, and online analyzer. Okay, the first one is offline instrument. Offline instruments are used in an environmentally controlled location. This instrument requires more time to be conducted compared to other options as it is conducted manually. For the inline instrument, it is a simple device that is placed directly into a process stream. They are used to measure pH, temperature, pressure, and density of substance. Next, proceed to the last options, which is online instruments. Online instruments is plumbed directly into the sample streams, with one instrument is used to monitor many samples. It can be used in filtration, cooling, pressure reduction, and heat tracing. There are many benefits of online measurement. Firstly, it provides higher level of consistency and certainty as the human factors is removed from the procedure. Besides, it is safer compared to other options because the persons do not have to collect samples or work with toxic reagents which may harm them. Okay, so this is the illustrations of at-line, online, inline, and offline in a factory process area.
Now let's talk about the light backscattering technique. This technique is used in the measurement of real-time particle size, and I'll be explaining briefly about the theory of light backscattering. So this technique uses a coherent light source, which in this case is the laser beam. Here you can see is the light source, and here is your sample medium, which we call as random medium. So as light is incident towards the random medium, the laser beam undergoes Brownian movement. So in this random direction movement, it exhibits the weak localization phenomenon. This phenomenon happens when there is a coherent interference between the scattered light and its time reverse counterpart. So here you can see the laser beam is moving randomly, and this A here is the scattered light and B is its time reverse counterpart. So due to this interference, the intensity of the backscattered light increases nearly twice as the diffused intensity within a small angular speed. So what light backscattering trying to show us is that when light is incident towards a random medium and undergoing Brownian motion, it experiences the weak localization, which results in the increase in intensity of the backscattered light. A common instrumentation used for this technique is the focused beam reflectance measurement (FBRM). So as you can see here, this is the probe of the FBRM, and this is what it looks like inside. So here is the laser beam being incident through a sapphire window towards the random medium and being backscattered towards the detector where the data is collected and integrated.
Okay, so what is crystallization? Crystallization is an important chemical operating unit widely used in the separation and purification of value-added pharmaceuticals, fine chemicals, and materials. Crystal size distribution is a vital property of crystalline products, since it can have impact on dissolution rate, processing ability, and drug bioavailability. There are two aspects that will be explained later regarding application of real-time particle size measurement in crystallization, which are potential and disadvantage. For the potential, real-time measuring device has a broad measuring range while only need a short time to analyze the particle compared to other technique of measuring particle size. There is no time delay even at extreme temperatures and pressure, because in online measurement, Any special sampling procedure is unnecessary before carrying out the particle size analysis. As the process of size measurement is simpler than other techniques, the risk of the operator to encounter dangerous situation is reduced. Because of real-time particle size analyzer is in situ instrument, no errors are introduced during the sampling, sample transport and sample preparation. As the feedback time is often instantaneous, it causes an immediate reacting to faults by additionally widening the databases. Even though it has many benefits in crystallization process, it also has some limitations. Firstly, the multiple scattering of the particles at high concentration affect the accuracy of the particle size distribution measurement. The fine particle may hinder the laser beam to the coarse particles. Next, the assumption of the crystal is a sphere by the measurement technique, which is not necessarily valid, especially for aggregates and more irregular shaped crystal. In addition, compared to an analytical sieve apparatus, laser diffraction instrumentation is also relatively expensive. Next, crystals which have small size less than 1 micrometer are difficult to detect by laser diffraction, as the laser can only detect the crystals with the size of 1 to 1000 micrometer. Furthermore, the probe or the focus beam reflectance measurement (FBRM) has the tendency to become fogged with small crystal particles.
Next is the application of real-time particle size measurement in semi-solid formulation. Semi-solid mentioned here is specifically emulsion. Emulsion is widely used in pharmaceutical industry. The droplet size of emulsion is important as it affects drug taste, consistency, performance, stability, as well as pharmacokinetics. Potentials of the application are: first, immediate and accurate emulsion droplet size measurement. Traditionally, the droplet size of emulsion is measured by using offline sampling method, where the sum of the emulsion needs to be diluted before droplet size could be observed. By using real-time particle sizing, the size of emulsion droplets could be determined along the process of homogenization without the need for sampling technique. Offline sampling can be unrepresentative as the sample will not be the same as the exact time it is taken. In real-time measurement, data and analysis are accurate as it represents the whole emulsion. Second, determine optimum type and amount of surfactant needed. Surfactant is an important element in emulsion formulation as it determines emulsion stability. In real-time measurement, the effect of change of surfactant, as well as reduction or addition, will be determined immediately by observing the data analysis. Third, reduce startup and operation time. The offline light diffraction instrument is traditionally take time to start and to be operated. The time to dilute the sample beforehand also contributed to the time taken, that usually will take hours, as the operator would have to take samples intermittently throughout the homogenizing process, whereas the real-time method only require the time similar as the homogenizing duration. Next, maximize the throughput of the emulsion. As there is no sampling needed, all of the emulsion is used throughout the operation, and the data obtained will be more accurate as more particles contributed in the process. Moreover, wastage could be avoided without sampling, as there will be no spillage as well as other errors. Lastly, detect perturbation and the vectors. From the data analysis, any changes that occurred throughout the emulsion formation could be determined. The trend of data could be observed if the find counts and the cause counts reduced or increased. If the change is caused by the variable manipulated in the process, the factors of perturbation could also be determined. The challenge of this application in emulsion formulation is the extremely high concentration of droplets during the homogenizing process that cannot be measured by laser diffraction without dilution. To cater this problem, the online or inline instrument is equipped with cascade diluter. This works as real-time diluter without any need for subsampling. The device is self-cleaning as well as providing real-time droplet size analysis.
Next, what is granulation? Granulation is a common technique for manufacturing solid dosage forms such as tablets and capsules. It is often necessary to convert powdered drug formulations into a physical form that has improved flow and compaction characteristic in order to produce tablets with uniform content and consistent hardness. Granule particle size and particle size distributions are important factors that affect granule flowability, tablet ability, and tablet dissolution rate. During granulation, powdered particles adhere to one another to form agglomerates and the size of the particles is increased. Focus beam reflectance measurement (FBRM) has been widely used for monitoring and controlling the granulation process. An at-line FBRM technique is used to monitor the granule growth and also used in line to follow particle size enlargement during high shear wet granulation. Moving on to the potentials of real-time particle size measurement in granulation. In or online measurement provides a platform for automated control in continuous granulation process. Therefore, an operator can instantaneously see the progress of the granulation and observe the effect of any operational changes made. The granule size at the endpoint of the granulation can be also precisely identified. In a batch process, it enables close monitoring of the process and the detection of the endpoint of the process. In pilot scale, the resulting secure process control improves data quality and experimental productivity. In commercial case, it helps to deliver the highest level of manufacturing efficiency. All in all, it ensures economic benefits by reducing waste, greater output, and high product quality. On the other hand, the major challenge of FBRM probe system is potential falling of the probe window by the dispersed material. If material sticks to the probe window, the same particles tend to be counted multiple times. To counter this problem, a self-cleaning spinning disk assembly was designed to minimize adherence of small particles to the probe window. A software called Midler Toledo FBRM C35 probe and IC FBRM have overcome this issue by including a scraper unit that keeps the probe window clean and provides software that corrects for multiple counting of any adhered particles.
In conclusion, particle size measurement is indeed gives many significance in pharmaceutical industry. The particle size distribution of active ingredients and excipients is an important physical characteristic of the materials used to create pharmaceutical products. The size, distribution, and shape of the particle size can affect bulk properties, product performance. The link between particle size and the product performance is well documented with regards to dissolution, absorption rates, and content uniformity. Next, the importance of the size particle is processability, stability, and appearance. In this project, we have highlighted three main applications of real-time particle size measurement in crystallization, semi-solid formulation, and granulation in terms of its potential and also the challenges. In short, those three applications have their own potentials and challenges, but in summary, the real-time particle measurement enables the faster and reliable process which will contribute to the higher accuracy of the particle size result, thus time saving. However, there are some challenges of using the real-time measurement of the particle size in using this application, which the most significant and the most obvious is that the probe of the instruments are very sensitive to certain conditions. For example, in the crystallization application, the probe may be blocked by the small particle. So overall, what would be our suggestions toward this application of the real-time measurement in the future? Maybe 5 or 10 years in the future, this type of particle size measurement can be applied to other various fields other than pharmaceutical field. Besides, it will produce much more accurate results with the improvement on design and quality of the probe or detector of the instruments, and of course with much lower cost.
Q&A session. Is there any other application that use real-time particle size measurement?
Yes, there is other applications which is in the drug coating process. The real-time particle size measures tablets during coating and the thickness of the coat can be correlated with the dissolution profile of the product.
Why people still use offline or traditional technique instead of real-time particle size measurement?
This is because the price of the real-time instrument is quite expensive. The range of the instrument price started from 50,000 ringgit.